We're at energy for the final couple of weeks here. I'm gonna use the restroom real quick. Right back. We'll start in a minute. You guys think about what you want me to say. Welcome back. So let's talk about L'Hopital's rule. L'Hopital's rule. Personal point of preference, say L'Hopital. Don't say La Hospital. That just sounds so wrong. It's correctly pronounced L'Hopital. So here's what we've got. If f of x and g of x are both differentiable, then we can say the following. If the limit as x approaches a of f of x over g of x is either equal to a 0 over 0 or an infinity over infinity, It doesn't matter what sort of infinity. It can be plus infinity on top, minus infinity on the bottom, minus plus, plus minus, doesn't matter what the signs are. Some sort of infinity, so it can be a plus or minus up here, plus or minus up here. Then we can say that that limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of the derivative of f of x over the derivative of g of x, provided this exists. So if you do L'Hopital's rule for something and you get a limit that doesn't exist, you kind of have to go back to the drawing board. Okay. We typically don't prove this in this class. It's kind of complicated. One way to think about why this might work the way it does is to consider the following thought experiment, for lack of a better word. It's kind of not bright. Okay. Here's the attendance form, by the way. So think about if you had two cars traveling. You've got, say, car A, this, and draw a car, kind of, and you've also got car B, smaller car, go slower. Okay, and we're going to say that A of t is the distance that car A has traveled. And naturally, if some function representing distance over time, or distance as time progresses, then its derivative is the velocity. Similarly, b of t is the distance of car B, and b prime of t is the velocity. Okay, here's where things get weird. You don't need to write this down. You can not write this down at all. Like you can, I mean, you can if you want to, but you don't need to write this down. So we're gonna say, suppose both cars travel for an infinite amount of time. And over this time, or I guess you could say at the end of an infinite amount of time, which sounds like a dumb thing to say. But the point is that over this kind of thing that's happening, we're going to say that suppose car A travels twice as far as car B. First of all, if they both have some non-zero speed, right, they're both going to travel an infinite distance, right? If you keep going forever and ever and ever at some speed, you're going to go forever. So check this out. What we're going to say is the limit as t goes to infinity of the distance that A traveled divided by the distance that B traveled, even though it's an infinity over infinity, right? A travels infinite feet or miles or whatever. B travels infinite miles. A is traveling twice as far. So this limit should equal 2. So far, we haven't really said anything. I'm just kind of making stuff up so far. You're like, so there's nothing to have missed so far. We're just saying, yeah, we're saying A traveled twice as far as B. So that limit as time goes towards infinity, if A traveled twice as far as B, then the distance A traveled should be twice as much as the distance B traveled. And so this fraction should get closer and closer and closer to 2. But now if we think about these cars driving forever and ever and ever, and A went twice as far as B over this quote-unquote time period, what it kind of means is that A had to be driving twice as fast as B the whole time. Right? If I drive for infinity and I'm going twice as far as someone else driving for infinity, I had to have been driving twice as fast almost the whole time to have covered twice as much distance in the same amount of time. So what we're saying is this also kind of means, and that's how you write a B, right? A D. And we can also see or suppose that A must have been driving twice as fast. to cover twice as much distance in the same amount of time. Or in other words, the limit as t approaches infinity of the speed of car A over the speed of car B must also be 2, because A had to have been driving twice as fast to cover twice as much distance. This is by no means a proof of L'Hopital's rule, but it's kind of just an idea to help you kind of maybe have a better sense of why it might be true. That's kind of all there is to say about that rule.
The definition of the rule, when you say doing it as x approaches infinity of the prime of x.
Where did I say that?
After
I never said infinity.
x approaches a.
Okay.
X approaches a of the prime of x divided by g prime of x must exist. Do you
Right.
mean that they can't be infinity?
No, they can be infinity, but I'm saying if so, you might get to a point where you apply L'Hopital's rule to something, and then the subsequent limit doesn't exist.
But could the subsequent limit have infinity at the top, for example?
Sure, yeah.
And then the subsequent limit would be infinity. That would mean the first limit was also infinity.
It might,
Okay.
but it might also mean the first limit did something else. So
could be applied again.
well, if it's infinity over infinity, sure. But infinity on top is different than infinity over infinity. So yes. Really, the kind of what ends up happening every time you apply L'Hopital's rule, you then immediately check to see, okay, if I take the limit of that, do I get something that makes sense, or do I have to do something else? Let's look at some examples. So let's look at, say, the limit as x approaches infinity of x squared over e to the x. And you should always think about it. So if you're thinking about using L'Hopital's rule, you should first think about, can I use L'Hopital's rule? What kind of indeterminate form is this, or is it an indeterminate form? So in this case, I have an infinity over infinity. Great, so I can use L'Hopital's rule. So using L'Hopital's rule, I like to write a little L apostrophe H when I use L'Hopital's rule. The derivative of the top is 2x. The derivative of the bottom is still e to the x. It's still an infinity over infinity type. So I use L'Hopital's rule again. If the limit as x goes to infinity of derivative of 2x is 2. Derivative of e to the x is still e to the x. And now I check, and I don't get infinity over infinity. I get 2 over infinity, which is very, very, very small. This is going to end up being 0. So my limit is equal to 0. And noteworthily, something of note, you could probably see that this would be true no matter how large a power of x I picked, right? This would be true for, you could say, the limit as x approaches infinity of x to any positive power over e to the x. P is a positive integer power, I should say. Yeah.
So you're saying e to the x goes faster than x to any power?
I am saying that. I'm exactly saying that. I'm saying e to the x, the exponential function, is faster growing than any polynomial function. Do you disagree?
I'm thinking about it.
So if you were to graph, for example, like x to the 100th power versus e to the x, in the beginning, x to the 100th would be way, way bigger. In fact, we might as well look at it because we can. Can we? Maybe. So here is good old e to the x. It's big fast. Here is something not that exciting, x squared. It gets big. It starts off not bigger. In fact, it never even gets bigger. It's always going to be outclassed by e to the x. But if you do x cubed, okay, it's kind of big. And the thing is, it's kind of hard to see here because of how steep things are. But eventually, e to the x is bigger. And I wish I could But I could do something here to make it. Let's see, I want my x-axis to be wider. Let's say from here, 0. Making this like 10. 10's pretty big. Let's try 5. Okay. Cool. So look at that. You can see that while the blue one x cubed passes e to the x, eventually e to the x is going to pass it again. And that's going to be true no matter how big your power is. Now it's going to look ridiculous if I pick something large, right? So here it's hard to see and you have to start zooming out. And eventually, oh yeah, e to the x is going to make the cross, right? It's going to eventually pass it. So no matter how big your power is, eventually e to the x is going to overcome it. And the more straightforward way of showing that is by, is by looking at something like this and saying, oh yeah, well, if I just keep applying L'Hopital's rule, the derivative of e to the x is always e to the x. The denominator is just going to stay the same. Whereas every time you take the derivative of x to the p, the power is going to get 1 less. And eventually you're going to get to a point where you're going to have a derivative that's just a constant term. So, after you apply L'Hopital's rule, p times, you're going to get the limit as x goes to infinity of p times p minus 1 times p minus 2 times p minus 2, all the way down to 3 times 2 times 1, all over still e to the x. And as x goes to infinity, this constant, although it's big, it's p factorial, is still not as big as something that's getting infinitely large. So that's going to be 0. Kind of neat. In a similar way, you can see that, say, the natural log of x is always outclassed by, say, a square root of x. I know from experience that the square root of x or any root of x is always going to overcome a natural log. Think about the graphs for a second. Even though they both kind of grow slowly, the square root graph grows faster than the logarithmic graph. The logarithmic graph looks like it's kind of more flatter, although it's not really flat. You can also see it here. If I use, well, first of all, this is an infinity over infinity type. I'm going to use L'Hopital's rule. I like writing little quotes here. This is going to be equal to the limit as x goes to infinity. Let's actually rewrite it first as the natural log of x over x to the 1/2. And then if I apply L'Hopital's rule, be careful. When you're applying L'Hopital's rule, you're just taking it's easy, right? It's easy in that you're just taking the derivative of the top, the derivative of the bottom. You're not using the quotient rule, which I've definitely seen students doing in the past. So make sure you're not using the quotient rule. You're saying, oh, the derivative of the natural log of x is 1 over x. The derivative of x to the 1/2 is negative x to the negative 1/2. Sorry, negative 1/2 x to the negative 1/2, or negative 1 over 2 root x. And here's where we have to be careful. If you try evaluating the limit right now, you might end up convincing yourself you need to use L'Hopital's rule again. If you plug in the infinity right now, you get 1 over infinity, which is a 0, over 1 over 2 root infinity, which is also a 0. And the 0 over 0 means we could use L'Hopital's rule. Just because you can do something doesn't mean you should do something. Here we definitely don't want to use L'Hopital's rule. What we should do instead, live transfer, sure, definitely. Yes, yeah, totally. So just because we can use L'Hopital's rule sometimes doesn't mean we should. Here what we should do is simplify. We're definitely going to rewrite this as the limit as x goes to infinity of 1 over x times negative 2 root x over 1. Or simplifying, that's going to be the limit as x goes to infinity of negative 2 over the square root of x. And that's just 0, because the denominator is getting infinitely large. And this would end up being true no matter what your root was. It could be the square root or the cube root or the 4th root or the 100th root. The same, in fact, let's check. What's the limit as x goes to infinity of the natural log of x divided by the 100th root of x? The same sort of thing is going to happen. we're gonna use L'Hopital's rule because we know it's an infinity over infinity. Important to know, natural log of something that's getting infinitely large does get infinitely large. I think if you think about the graph of the natural logarithm, let me draw it over here real quick. If you think about the graph of the natural logarithm, it looks like this. So it's really important to know, I've kind of exaggerated it, that it gets infinitely large as you go off to infinity and negatively infinitely large as you go closer and closer to zero. So here, we're going to use L'Hopital's rule. The derivative of the natural log of x is 1 over x. The derivative of x to the 1/100th power is 1/100th times x to the 1/100th minus 1 is negative 99/100. This is where we should simplify. If all of your things are powers of x, it's weird to see sorry, someone asked me to turn on the live transcription. I can see the words I'm saying coming up on the screen. It's kind of distracting. I'm like, oh, okay, all right. So anyway, if we simplify this, which we should always try to do if we have just powers of x, I'm going to write this as the limit. We should always be writing the limit until we take the actual limit. Dividing by 1/100th is like multiplying by 100. And then I've got 1 over x times x to the positive 99 over 100. Or in other words, the limit as x goes to infinity of x to the 100 times x to the 99/100th over x to the 1 is going to be 1 over x to the 1/100th, which that'll go to infinity, so the whole thing will go to 0. So just like an exponential will always overpower a polynomial, a root will always overpower a logarithm, which kind of makes sense if you think about it because they're actually inverse functions. Logarithms are inverses of exponentials and roots are inverses of polynomials. So they're their relationship to each other switches when you invert them. Yeah.
So does that mean if we have them times each other, so if you have, I don't know, if it's times a root, and we are looking at the limit as approaching 0 from the right, does it always equal 0?
That's a good question. I don't know. We'd have to check it out. So what if we wanted to find the limit as x approaches 0 from the right of the cube root of x times the natural log of x? So I'm going to be super extra clear. This is not necessarily equal to 0 just from the get-go. Because if we plug in 0, we have a 0 times the natural log of 0 goes to negative infinity. And what's 0 times infinity? I don't know. It's an indeterminate form. So far, just, right, 0 times infinity is also an indeterminate form. Just like 0 over 0 or infinity over infinity. The difference is we can't apply L'Hopital's rule to it without manipulating it first. So I want to really heavily stress, you can only use L'Hopital's rule if it's 0 over 0 or infinity over infinity. We cannot use L'Hopital's rule on any other type of indeterminate form until we have first worked on it. So here, I need to do something. I need to rewrite it. I'm going to rewrite it as the limit as x goes to 0 from the right. You can bring either thing to the denominator as its reciprocal. I would usually encourage to bring the less complicated thing to the denominator, meaning I could write it like this, natural log of x over 1 over the cube root of x, or I could, although I'm not going to, write it like this. Limit as x goes to 0 from the right of the cube root of x over 1 over the natural log of x. Both are technically options. Both have the quote unquote correct form. If x is going to 0 here, you've got a negative infinity over an infinity, because natural log of 0 goes to negative infinity. And the cube root of 0 is 0, and 1 over 0, since it's a positive 0, goes to positive infinity. So here we could totally use L'Hopital's rule. We also could here, technically. Here, this is a 0 over 0 form. Cube root of 0 is 0, and natural log of 0 going to negative infinity, 1 over that goes to 0. Which kind of makes sense if you think about it. right? If you have a 0 times infinity, what you're really doing when you rewrite this is you're either rewriting it as infinity over the reciprocal of your 0 thing, which is like an infinity over infinity, or you're rewriting it as 0 over the reciprocal of your infinity thing, which is like a 0 over 0. So that's why whenever you have a multiplication where it's like a 0 times infinity, you're always taking one piece and dividing by its reciprocal. But you have to make sure that I see people a lot of times miss the reciprocal part. So make sure it's the reciprocal. And you want the thing in the denominator to be easy to take the derivative of. 1 over natural log of x is kind of a pain. I don't want to take the derivative of 1 over natural log of x. It's not going to be nice. I'm going to do the chain rule. Here, I can totally rewrite this as just the limit as x goes to 0 from the right of the natural log of x over x to the negative 1/3. That's going to be much easier to use L'Hopital's rule on. So now I'm going to do it. So it's going to be the limit as x approaches 0 from the right. The derivative of the natural log of x is 1 over x. The derivative of x to the negative 1/3 is negative 1/3 x to the negative 4/3. Once again, we're in a case where we have just essentially powers of x. We should definitely simplify. So I'm going to rewrite this as the limit as x approaches 0 from the right of negative 3 times x to the negative 1 times x to the positive 4/3, which ends up being the limit as x approaches 0 from the right of negative 3 times x to the positive 1/3. And I can plug in 0, and 0 to the 1/3 is just 0. So it is 0. Question? Mm-hmm.
So infinity is just a big number.
Right.
Any number, any real number times 0 is just 0.
That is true. Any real number times 0 is 0. But so here's my counter argument to what you're about to say. This isn't 0. This is really just a small number. You said, right? You said this isn't really infinity. It's really just a big number, and you're right. But I will also say this really isn't 0. This is really just a small number.
About the question is how which one is a smaller, which one is bigger?
Right. It's all about the push and pull. Which one is overpowering? And sometimes the 0 wins. Sometimes the infinity wins. Sometimes they balance each other out, and you meet somewhere in the middle. So that's what's really kind of happening. So in fact, I want to kind of expand on that for just a second. When we write these things like 0 times infinity, you really shouldn't read them that way. When we write 0 times infinity, we really mean a small number times a big number. Right, exactly. The thing's getting really, really close to 0. It's not actually 0, but we still call it a 0 times infinity type of indeterminate form. And we're going to see that for some other things as well. Just like infinity over infinity really just means a big number over a big number. And 0 over 0 really just means a small number over a small number. Okay, good question. Good. Something else.
Just one quick follow-up question.
Mm-hmm.
So I get that from the way you explained it, but
Sure.
how about infinity over 0?
That's not an indeterminate form.
It's not.
That is a very well-determined form.
It's just infinity or negative or positive.
Right, or maybe it doesn't exist if the both sides don't match up.
Sure. If you're looking at one side of the
Sure.
thing, it's just
Yeah, exactly. So for example, if you were going to find the limit as x approaches 0 of, say, sine x over x, well, we know this limit should be 1 from way back when. But you could also just do it by using L'Hopital's rule. You get the limit as x approaches 0 from the right of the derivative of sine x is cosine of x. The derivative of x is 1. And then you can just plug in 0 and get cosine of 0 over 1, which is 1 over 1, which is 1. On the other hand, if someone said, what's the limit as x approaches 0 from the right of cosine of x over x, we cannot use L'Hopital's rule. So we plug in 0 right now, we get a 1 over a 0. Over a slightly positive 0. Or as I say, a 1 divided by a very, very small positive number. And 1 divided by a very small positive number is a very large positive number. So in this case, L'Hopital's rule cannot be applied. Well, you're right. So technically this limit doesn't exist, but it doesn't exist in a very specific way. We know that this limit, as x gets closer and closer and closer to 0, this function is getting larger and larger and larger. So even though this limit doesn't exist, we say, well, it doesn't exist, and we know it's getting really, really big. So we say the limit is positive infinity. Right. So often we have to do some sort of algebraic thing to work with that. But that's more when it's a 0 over 0 type. If it's a non-zero number over 0, your options are very, very limited. You either get infinity or minus infinity, or it does not exist if both sides are doing a different thing.
And you would find that by this.
Let me show you another example. Let's say we want to find the limit as x approaches 3 from the left of 5 over x minus 3 quantity squared. All we're really going to do is plug in the 3 and see what happens. Just like you almost always should whenever you're, right? It's kind of like we've gone back to the beginning of the quarter, like we're still dealing with limits. Whenever you deal with a limit, the first thing you should do is try plugging in the value that x is approaching and see what you get. By plugging in 3 here, what do I get? 5 over 0 squared, right? So what I see when I see my 5 over 0 squared, if you like, what I see is a not 0 over 0. When I have not 0 over 0, I know the limit doesn't exist, but I know it might be some sort of infinity because it might be getting infinitely large or negatively infinitely large. And here, well, I'm approaching 3 from the left. I'm a little bit less than 3. A little bit less than 3 minus 3 is slightly negative. Slightly negative squared is slightly positive. 5 divided by a very, very, very small positive number is a very, very large positive number.
Okay, so when you end up with that, you look at which side you.
Right, right. Trying to look at the overall sign.
Yeah.
Right, because if this had been a negative 5 over x minus 3 squared, then my answer would have been negative infinity. It would have been negative over a positive. But yeah, when you get not 0 over 0, it's always some sort of infinity or non-existent. Did you have a question, Manny?
Really quick question, since we haven't done this since the beginning of the course, could you remind us of when the limit doesn't exist? Like any example?
Oh, sure. So an example of limit not existing would be a two-sided limit. Well, I should say this type of non-existing, because there are other types of non-existing. For example, a limit could not exist if someone said, what's the limit as x goes to 0 of sine of 1 over x? That limit does not exist. Oscillates back and forth forever and ever and ever. Let's go from the right, just to be specific. But another example, the example I think you're actually asking about is something like the limit as x approaches 3 again of 6 over x minus 3. Because that's a two-sided limit, and the right side, the limit as x approaches positive 3, is going to be 6 over a slightly positive 0, which is positive infinity. Whereas the left-hand limit, as x approaches 3 from the left, of 6 over x minus 3, is going to be 6 over a slightly negative small number, which is going to be negative infinity. And since these two limits both don't exist in different ways, right? The one's going infinitely large, one's going infinitely small, or negatively infinite. The overall limit does not exist because the right side and the left side are doing different things. Cool. Okay. Let's talk about another example that so just a couple more examples to kind of remind us or confirm to us that things are actually working how we think they should. The limit as x approaches infinity of 6x squared plus 5x plus 4 over 3x squared plus 2x plus 1. Each and every one of you, I think, should be able to tell me that this limit, actually show me on your fingers or type in the chat. What is this limit equal to? Without using L'Hopital's rule. Fingers. Yeah, thank you. Yes, exactly. It's equal to 2 because it's equal to 6 over 3, which is just the quotient of the leading coefficients when the degrees are the same. But you could also use L'Hopital's rule here. You don't really need to, but you could say, well, this is going to be the limit as x approaches infinity of 6x squared plus 5x plus 4 over 3x squared plus 2x plus 1. It's definitely an infinity over infinity type. Top's certainly going to infinity, bottom's certainly going to infinity. So if we use L'Hopital's rule, we get the limit as x goes to infinity of 12x plus 5 over 6x plus 2 Still an infinity over infinity type. So I use it again. And you get the limit as x approaches infinity of 12 over 6, which is the limit of 2, which is 2. So certainly there are times where you can use L'Hopital's rule, even though you don't necessarily have to, right? You totally could have evaluated this limit without using L'Hopital's rule at all. You could say it's 2. Or you could do the thing where you divide everything by x squared. That's also what you could do here. Never kind of that one. Come on. And kind of to your point, it also, we can use it for things where we would have used algebra. For example, if I was going to find the limit as x approaches 2 of x squared plus 3x minus 10 over x squared minus 4, if I plug in that 2, I get 0 over 0. Okay. Well, I could factor and cancel. Factoring and canceling isn't so bad here, right? I could say this is equal to the limit as x approaches 2 of, let's see, the top is going to factor as x minus 2 times x plus 5. And the bottom is going to factor as x minus 2 times x plus 2. And then those cancel, and you plug in 2, and you get 7 over 4. But we also could use L'Hopital's rule. We could have said, well, this is equal to, using L'Hopital's rule, the limit as x approaches 2 of 2x plus 3 over 2x. And now here's where you need to be extra careful. People see this and sometimes think I should just do it again. But every time after you use L'Hopital's rule, the first thing you should do is try to plug in what x is approaching. So I plug in x equals 2, what do I get? 7 over 4. Oh, yeah. That's a good question. Some people get caught up. I've seen students look at this and kind of think of it, they've thought of it more as like a limit as x goes to infinity. So I've seen people like do this and end up getting an answer of 1 because they weren't paying attention to what x was approaching. Right, exactly. So it's really, really important to be careful about where is x going to and actually think about plugging that in every time we do it. So like here, I plugged it in, I got 0 over 0. I did it this way, okay, I got something. I did it this way, and then after my first step, I tried plugging it in. So every time after you use L'Hopital's rule, the first thing you really should do is check to see, can I now plug in what x is approaching and get a real number result? Or am I still getting a 0 over 0 or infinity over infinity?
Earlier you said that if you have non-zero divided by 0, it might approach infinity. Doesn't it always approach infinity?
By approach negative infinity.
Infinity or negative infinity, but it has to be an asymptote, right?
Yeah.
Okay.
Yeah. Sure. What about something like, ooh, yes, a good one. The limit as x approaches 0 of 2 to the x minus 1 over 3 to the sine of x minus 1. The third, I don't think I could do algebraically. Right? You've got, well, first of all, let's check. Is it a 0 over 0 type? So we need to be sure that we actually are doing what we're doing. Let's see, 2 to the 0 minus 1 is 0. And 3 to the sine of 0 is 0. 3 to the 0 is 1. 1 minus 1 is also 0. So it's definitely a 0 over 0 type. So, all right, let's try using L'Hopital's rule here. So using L'Hopital's rule, it's gonna be the limit as x goes to 0. The derivative of 2 to the x, 2 to the x times the natural log of 2. And the derivative of 3 to the stuff, well, the derivative of 3 to the x would be 3 to the x times natural log of 3. The derivative of 3 to the stuff is going to be 3 to the stuff times the derivative of that stuff times the natural log of 3. That looks gross. But you know what it doesn't look like? An indeterminate form. If you plug in 0 here, you're just going to get a number. You're going to get 2 to the 0 times natural log of 2 over 3 to the sine of 0 is 3 to the 0 times cosine of 0 is 1 times natural log of 3, which ends up just being the natural log of 2 divided by the natural log of 3. Sure.
Wait.
Nope. Right. Sure, let's do a couple more before we start going in a different direction. Let's say we want to find the limit as x goes to 0 of sine of x minus x over x cubed. And definitely is a 0 over 0 type. Plug in 0 for the top, you get 0. Plug in 0 for the bottom, you get 0. So if I do this, let's see, it's going to be using L'Hopital's rule. The limit as x approaches 0. Let's see, derivative sine of x is cosine of x. Derivative of x is 1. Derivative of x cubed is 3x squared. Plugging in 0. Cosine of 0 is 1. 1 minus 1 is 0. I still get 0 over 0. I got to do it again. All right, so this, I should say, right, this is a 0 over 0. This is a 0 over 0. Do it again. You get the limit as x goes to 0 of, let's see, negative sine of x over 6x, which still is 0 over 0. Now, at this point, you could, if you wanted to, not use L'Hopital's rule again. You could say, hey, I see a sine x over x. I know that if x is going to 0, sine x over x goes to 1. So this would be a negative 1/6 times a 1. But we've already done the L'Hopital's rule 3 times. We might as well, sorry, 2 times. We might as well do it one more time. So we use L'Hopital's rule again. I get the limit as x goes to 0 of negative cosine of x over 6. And now I can plug in 0 and get negative cosine of 0 over 6, which is negative 1/6.
What was the limit of sine x over x again?
Ah, yes. So way back when, we learned that the limit as x goes to 0 of sine x over x is equal to 1. Or more generally, as some stuff goes to 0, sine of the stuff or the same stuff goes to 1. That actually comes up because I have certainly in the past, and maybe this was not the nicest question to ask ever, but in the past, I have asked students this question on the test. Find the limit as x goes to 0. Do I want to make it really hard? It's kind of really hard. Of sine of 2x cubed over 5x cubed. Is that what I really want? No, it's not what I really want. Sorry, that's too easy. Well, we can do this one. Sure, why not? Let's do this one, and then we'll talk about what I really need to do. So here, if I plug in 0, I get 0 over 0. I could probably do it a different way, but fine. Let's just use L'Hopital's rule. We do the L'Hopital's rule. The limit as x goes to 0 of, let's see, the derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff, which is 6x squared. Over on the bottom, the derivative of the stuff, which is 15x squared. Now, if I wasn't careful, I could think I might need to use L'Hopital's rule again. Because technically, if I plug in 0 right now, I get a 0 over 0. But what should I do? I should simplify. Right? Those x squareds definitely cancel. So definitely simplifying things that are easy to simplify should be done. And then this is just the limit as x goes to 0 of cosine of 2x cubed times 6 over 15. If I plug in 0, I get cosine of 0, which is 1 times 6 over 15, which reduces to 2 over 5. But that's not the question I actually meant to ask. Here's the question I meant to ask. Yes. The limit as x approaches 0 of sine cubed of 2x over 5x cubed. And all that problem looks innocuously similar. It is definitely very, 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 very terribly different. Let's try to use L'Hopital's rule here. So I should point out, you can use L'Hopital's rule here successfully if you are really determined to do it. You should not be. Let me show you why. We use L'Hopital's rule. The first step is not so bad. I'm going to take the limit as x goes to 0. The derivative of the top, okay, well, I have to use the chain rule here. I've got sine cubed of 2x, which is sine of 2x quantity cubed. So if I have sine of 2x cubed, or some stuff cubed, the derivative is going to be 3 times my stuff squared times the derivative of that inside stuff, which is cosine of 2x times 2. All over the derivative of the bottom, which is 15x squared. You might notice that this is looking terrible already. I could simplify this a tiny bit if I really wanted to, cancel a 3 here and a 3 here. But when I do the next iteration, oh, I should point out, if we plug in 0 at this point, we're still going to get 0 over 0. Because sine of 0 is 0 and 0 squared is 0. And the next iteration of L'Hopital's rule, 1 is terrible and 2 is not conclusive. If we do L'Hopital's rule again, it's going to be awful. And then we're going to have to do it even a third time to actually get to the answer, which is really, really gross. It can be done, right? It's not impossible to take the derivative of sine 2x squared times cosine 2x, but it's not fun. And I think in the derivative, that's even worse. So here's the thing. Even though you can use L'Hopital's rule here, we shouldn't. Not because we shouldn't, because we have another method that'll work for us. So if you can do something else when L'Hopital's rule might be terrible, then you are encouraged to do so. Here, I'll remind you of what we did way back when. I want to try to find the limit as x goes to 0 of sine cubed of 2x over 5x cubed. I'm going to write this as the limit as x goes to 0 of sine of 2x over nothing times sine of 2x over blank times sine of 2x over blank times blank over 5x cubed. And then fill in the blanks. What do I really want down there? It needs sine of 2x. I know it's been like 8 weeks. What's that? Yeah, I want 2x. If I put one there, I have to put one there. And same deal here. And same deal here. Because we know that the limit as x goes to 0 of sine of some stuff, I should say stuff there, over the same stuff. Those things need to be the same so that limit is equal to 1. Stuff. So that's what we're doing. We're making so that each of these sine of a thing over the same thing has a limit that's going to go to 1. So this is going to go to 1. This is going to go to 1. And this is going to go to 1. And these x's are all going to cancel. X times x times x is x cubed. And we're going to get 2 times 2 times 2 over 5, which is going to be 8/5. You can do this the long L'Hopital way if you want to, taking L'Hopital's rule 2 more times, and you will, assuming you don't make any mistakes, get 8/5. But it's not the way to do it.
Wait, can you say one more time how that cancels?
Which part cancels?
Like how you got 8/5.
Sure. So what I'm really doing here, I'm kind of abusing, no, not abusing. I'm not showing all the work. What I really should be doing is writing this as a bunch of limits multiplied together. Its limit as x goes to 0 of sine of 2x over 2x times the limit as x goes to 0 of sine of 2x over 2x times the limit as x goes to 0 of sine of 2x over 2x times the limit as x goes to 0 of 2x times 2x times 2x over 5x cubed. Right. So this is going to be 1 times 1 times 1 times 2x times 2x times 2x. Well, that's really just 8x cubed, and the x cubes cancel. So you end up with 8 over 5, which is 8/5. You have a question? Taking off, man? It's okay if you don't. You just looked. I saw a look on your face like maybe this is a question.
Oh no, I
Okay.
just got a different answer, but I.
Okay. Yeah.
Like actual log of like a number, like x or something. And
Wait, x or a number?
it was x.
Well, it really depends on what the question is. Continue.
And it was x. And then it was like, oh, that is squared.
So like you're looking at something like, say, natural log of x squared. Like maybe like, well, so, but I mean, like, are we taking maybe like, say, the limit as x goes to 0 from the right of natural log of x squared over. Sure. I'm going to make up something. Well, well, then let's sure if we do the limit to infinity.
Why you can have it too positive for that?
Well, no, well, so what I'm saying is if we were looking at this limit. We wouldn't use L'Hopital's rule. Right, because if you plug in 0, okay, I know this is not the best question ever to ask, but what does the natural log of x go to as x goes to 0? I really encourage everyone to try and have a picture of the natural log graph in their head. Say, okay, as we're going towards 0, what's happening to the logarithmic graph? Right, it goes to negative infinity. Right, here's our logarithmic graph. And as we approach 0, the values get more and more and more and more and more negative. So what this looks like here is it looks like something that's going to negative infinity squared over something that's going to 1. So this limit would be infinity.
Can you sketch the graph of e of x?
Sure. E to the x looks like this. Oops, kind of. So as we go towards 0, e to the x goes towards 1. Yeah. On the other hand, this here, we would definitely need to use L'Hopital's rule because you have an infinity over infinity. Now I can tell you for sure that this limit's going to be 0. The reason it's going to be 0 is because e to the x is getting bigger way, way faster than the natural log of x ever could, or the natural log of x squared. But if we use L'Hopital's rule, which we kind of have to still, we're going to get the limit as x goes to infinity. The derivative of natural log of x squared, you're right, we have to use the chain rule. It's some stuff squared. The derivative is 2 times our stuff to the first times the derivative of the stuff. And the derivative of e to the x is e to the x. So now this is kind of interesting. Because as is, it's not really a L'Hopital's rule of question in its current state. Because you have the top natural log of x is going to infinity. 1 over x is going to 0. So you have infinity times 0 over infinity. We should definitely rewrite this so we can use L'Hopital's rule. So if I actually want to use L'Hopital's rule again, I need to rewrite this in the following way, in my opinion. Write this as 2 times natural log of x over x times e to the x. Because now the numerator is for sure going to infinity, and the denominator is for sure going to infinity. So then we can use L'Hopital's rule. And the limit as x goes to infinity. The derivative of 2 times natural log of x is 2 times 1 over x. And the derivative of x e to the x is product rule. 1 times e to the x plus x times e to the x. And now for sure, as x goes to infinity, the top is going to 0. The bottom is going to infinity. That's definitely 0. 0 divided by a really large number is for sure 0. I had one other good one. Yeah. Sometimes people will ask questions in this sort of vein in the following way. Find the horizontal asymptotes. Come on, can I write? Maybe. Of the following function. F of x equal to, I forgot what it was. I think it was 5x plus e to the 4x, or 4x plus e to the 5x. Is that what it was? That's close enough, yeah. So how do we find horizontal asymptotes? Well, the idea with the horizontal asymptote is we're just asking about the behavior of a function as x gets really, 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 really large, or really, really, really negatively large. So if I want to find the horizontal asymptotes, I'm going to take the limit to infinity. And then I'm going to ask myself, okay, well, it looks like an infinity over infinity. The top certainly, right? 5 times infinity plus e to the infinity is definitely infinity. 4 times infinity plus e to the infinity is definitely infinity. So this is definitely an infinity over infinity. I'm going to use L'Hopital's rule. So let's see, I'm gonna get the derivative of 5x is 5, the derivative of e to the 4x is 4 e to the 4x over 4 plus the derivative of e to the 5x is 5 e to the 5x. Still infinity over infinity. I guess I better do it again. So then I'm gonna get the limit as x goes to infinity. Derivative of 5 is 0. Derivative of 4 e to the 4x is 16 e to the 4x over derivative of 5 e to the 5x is 25 e to the 5x. And now I've got infinity over infinity again. And at this stage, we can probably see that if we keep doing L'Hopital's rule, we're just going to keep getting infinity over infinity. We're not right. These are both going to just be, we're going to get another, right, 16 times 4 over 25 times 5 times another 4 times another 5 and so on and so on and so on. So here is where we have to simplify. Because e to the 4x divided by e to the 5x, we could totally rewrite this as, not using L'Hopital's rule, the limit as x goes to infinity of 16 over 25 e to the x. Because we bring that e to the 4x down, e to the 5x times e to the negative 4x, or e to the 5x minus 4x is just e to the x. And then that limit's for sure going to be 0. Because the bottom's getting really, really big. This is a 16 over infinity. Which is 0.
Can you do a reminder of, okay, so it was e to the 4x, and then the derivative of that is like 4 e to the 4x. So for like the derivatives of e where it's not just e to the x and there's like something else, it's not just like e to the, oh, because it's e to the, and then it's the derivative of whatever is on the top.
Exactly. Right. I would remind you that the thing you're saying is more generally the derivative of e to the stuff is e to the stuff times the derivative of that stuff. Okay, now normally this isn't an issue, but it is here. We might have a different horizontal asymptote to the other side. So we look at the limit as x goes to negative infinity of 5x plus e to the 4x over 4x plus e to the 5x. So first of all, is this an infinity over infinity type? Well, 5x is certainly going to negative infinity. What about e to the 4x? Where's that going to? Yeah, it's going to 0. But we still have an infinity over infinity because we have an infinity plus 0, or I should say a negative infinity plus 0 over a negative infinity plus 0. So this is certainly a negative infinity over negative infinity indeterminate form. So we can certainly still use L'Hopital's rule and get the limit as x goes to minus infinity. Same derivative on top and bottom. It's still going to be 5 plus 4 e to the 4x over 4 plus 5 e to the 4x. And now we're pretty much done. We can't use L'Hopital's rule again because we don't have an indeterminate form. The top is going to 5 plus 4 times 0 over 4 times 5 plus 4 plus 5 times 0. The limit's 5/4. Because this part right here, that goes to 0 as x goes to negative infinity. Right, here's the graph. Here's e to the x or e to the 4x or whatever you want to think of it as. As you go to infinity, sure, it goes to infinity. As you go to negative infinity, the graph gets smaller and smaller and smaller. Yeah, I mean. So when we take the limit as x goes to infinity, if we've got this 2 over x here, we can write this we can think of this as 2 over x, and as x gets really, 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 really large, we think of 2 divided by x as getting really, really small. So we say the limit is going to be 0. Cool. Let's see what else. Okay, so one more time, right here. Mm-hmm.
Does it not work?
Well, so at this point, I don't have the right kind of indeterminate form. Because if I think about plugging in infinity, here's what I've got. I've got 2 times infinity times 1 over infinity over infinity. And the problem is, I want just an infinity over infinity or a 0 over 0. And here I kind of have like an infinity over infinity over infinity, which is weird. So I needed to rewrite it in this way, right? I brought this 1 over x down to the bottom so that then I could think of it as just infinity over infinity, and I can use L'Hopital's rule. Oh, yeah. So not all of our L'Hopital's rule questions are going to be given to us in a infinity over 0 over 0 kind of way. Sometimes we're going to have other indeterminate forms that we have to first manipulate. Like, for example, I don't love that example. The limit as x goes to, sure, not this example, infinity of x times e to the negative x. That's certainly an infinity times 0 indeterminate form. And again, right, so to echo what we were saying before, not really infinity times 0. It's really a big number times a small number. And we're trying to figure out what's happening to this big number times a small number. Is it going to be really big? Is it going to be really small? Is it going to be somewhere in between? So in this case, let's find out. Well, I'm going to rewrite this. Now, you always have a couple choices. Here are our choices here. So you could either write this as the limit as x goes to infinity of e to the negative x over 1 over x, or you could write it as the limit as x goes to infinity of x over 1 over e to the negative x. Now, although the second one looks worse, it actually isn't, because we can write this as the limit as x goes to infinity of x over e to the positive x. And that's typically what we should do. You could do it this way, but I don't think it actually works out. Right? If you try doing it this way, it's gonna get worse and worse and worse. Let me show you what I mean. If you try, so this is a 0 over 0. Right? E to the negative infinity goes to 0, 1 over infinity goes to 0. If you try using L'Hopital's rule here, look what happens. And you don't need to write this down. I just want to show you. But use L'Hopital's rule. The derivative of e to the negative x is e to the negative x times negative 1. And the derivative of 1 over x, which is x to the minus 1, is negative x to the minus 2, which is negative 1 over x squared. That hasn't gotten better. The top's still going to 0, the bottom's still going to 0. And in fact, the more I keep doing it here, I'm just going to keep getting 0 over 0, because the derivative of this is just going to get higher and higher powers of x. And right, I'm going to get like 2 over x cubed, and then 6 over x to the 4th, and so on. This is not going to get better. So typically, the choice that's the wrong choice is going to be so wrong that you're never going to be able to recover often. So we don't want to go this way. We want to go this way, because then we can say it's the limit using L'Hopital's rule as x goes to infinity of 1 over e to the x, which is just 0. I don't think you need to. Some people like to write. I don't particularly care to write that this is like, some people say this is 1 over infinity and that's 0. I think you can just write that it's equal to 0. All right, let's look at this example. I like this next example. Let's say we want to find the limit as x goes to infinity of x squared times sine of 1 over x squared. First of all, is it what we're looking for? Well, I mean, no, actually, it's not. It's not infinity over infinity or 0 over 0. But is it an indeterminate form? For sure it is, because if x is going to infinity, x squared is going to infinity. And if x squared is going to infinity, 1 over x squared is going to 0, and sine of 0 is 0. So we have another infinity times 0 form, or another big number times a small number form. So we're going to rewrite it. Okay. Which thing should I take the reciprocal of and bring to the bottom? Yeah, or you can write 1 over x squared, either way. So you can totally write this as the limit as x goes to infinity of sine of 1 over x squared over 1 over x squared. Or you might prefer to write it as the limit as x goes to infinity of sine of x to the negative 2 over x to the negative 2. Either way, we can see it's a 0 over 0 form. The top is certainly going to 0. the bottom is certainly going to 0, which means we are allowed to use L'Hopital's rule. Using L'Hopital's rule. Now, here's something to think about as we do this. When I take the derivative of sine of some stuff, I'm going to get cosine of the stuff times the derivative of that stuff. And on the bottom, I'm going to get the derivative of that same stuff. Those two derivatives are going to cancel each other out because they're going to be exactly the same. Here's what I mean. When I take the derivative of here, I'm going to get, well, sorry, when I use L'Hopital's rule and take the derivative of the top, I'm going to get cosine of x to the negative second times the derivative of x to the negative second, which is negative 2x to the negative third, over the derivative of x to the negative second, which is negative 2 times x to the negative third. And those are definitely for sure just going to cancel out. I should cancel out things that are definitely the same. So then I'm left with the limit as x goes to infinity of, I would certainly write this as cosine of 1 over x squared. Because for me, it's easier to see that if x is going to infinity, 1 over x squared is going to 0. Whereas it's not as easy for me to see that x to the negative 2 is going to 0 in that case. Even though I know they're the same, it's easier for me to see that this is 0. So this is going to be cosine of 0, which is 1. Yeah, I mean it. So we're using L'Hopital's rule, which you weren't here at the beginning. So let me remind everybody. L'Hopital's rule says the following. Right, I'll just write it again. So L'Hopital's rule says that the limit as x approaches a, I should say if limit as x approaches a of f of x over g of x is either 0 over 0 or infinity over infinity, then we can say the following. The limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. That's what L'Hopital's rule says. So that's what we're doing here. We're taking our top function and taking its derivative, and getting cosine of x to the negative second times negative 2x to the negative third, and the bottom function taking its derivative. That clear things up a little bit? Yeah.
The graph of sine of something over sine of that same something, isn't that gonna look the same? So like as it approaches 0, it's at 1, but as it approaches like infinity or negative infinity, it approaches 0. How does this? So you're on the right track, but there's a slight kind of hiccup in what we've done here versus what you're not wrong to say what you're saying, but let me remind. So here's what you've got. This totally should be 1, and the reason is because I'm taking the limit. I'm gonna say, here's what I'm gonna say. I'm taking the limit of sine of some stuff or the same stuff. And where is that stuff going to? Where is that stuff going to? As x approaches infinity, where is that stuff going? Right. And that's the whole thing we've said before. If you have sine of a thing over the same thing, and those things are going to 0, then that limit's equal to 1. We've usually said it more like this, right? We've usually said the limit as x approaches 0 of sine x over x is equal to 1. But really what matters is that this and this are the same, and they're both going to 0. Right, exactly. That's a very excellent observation, that the limit as x goes to infinity of sine of 2x over 2x is definitely not 1. Well, it goes to 0, right?
Right, but how do we know? How do we show that? You're right. And the way we show it is by using everyone's favorite theorem, maybe not your favorite. Yeah. So we say here that sine of 2x is between negative 1 and 1. Then we divide everything by 2x. And then we say the limit of that's 0 and the limit of that's 0. So the limit of that must be 0.
For sine of 1 over x over 1
So let me see. Sorry, let me finish writing this just so that it feels complete here. My get is no, though. So, because I think it's pretty much the same problem we just did. Let's clarify. When you say, it depends on what x is approaching, I think. So if we're finding the limit of sine of, what was it, 1 over x over 1 over x, where's x going to? Well, that's what I'm asking you. What do you want me to, like, what are we trying to look at? Sure, it's going to infinity, then that's going to equal 1. And the squeeze theorem is not going to help us. Here's why the squeeze theorem is not going to help us. So squeeze theorem is no help because what we're really looking at is the limit as x goes to infinity of x times sine of 1 over x. It's for sure true that sine of 1 over x is between 1 and -1. But if you multiply everything by x, and then take the limit as x goes to infinity, well, that's going to go to infinity, and that's going to go to negative infinity. Since they aren't going to the same thing, this isn't getting squeezed between them to the same value. On the other hand, if you did the limit as x goes to 0, you for sure could use the squeeze theorem. So just like, well, so if you want to find the limit as x goes to 0, I would write it as x times sine of 1 over x. That is going to be 0 by the squeeze theorem. Fair questions.
The sign of stuff over stuff when you took the limits in there before.
It's a slightly more, I want to say complicated. It's slightly more nuanced than that. So, and I think were you just using the restroom for that or out of the room? Yeah. So what it actually is that it's, if you have sine of some stuff over the same stuff, that stuff has to be going to 0. But that stuff might not mean that x is going to 0. So we need the stuff going to 0. And that's what's happening here. Stuff, same stuff. And where is that stuff going to as x goes to infinity? 0. So that's the deal, is the stuff that you're taking sine of and the stuff you're dividing by has to somehow be getting closer and closer to 0. And then that limit will be 1. In a similar way, I can write something silly like the limit as x approaches 2 of sine of 2 minus x over 2 minus x. That meets all the criteria. The limit is for sure 1. Here you could easily use L'Hopital's rule though. Here you could also use L'Hopital's rule. Right? They're both 0 over zeros. But you could also use the rule that we know from before. Sure.
Oh, yeah, sure. Yeah.
Mm-hmm.
After the or, but it's like limit as x.
Right. I'm just saying you can write it either way. These are the same.
Yeah, okay. How is, if it's x to the -2 and it's x going to infinity, how is that 0?
That's why I like to write it as 1 over x squared.
Okay.
It's the same thing, but it's much easier for me to say, okay, yeah, I know that 1 over x squared is the same as x to the -2, but it's much easier for me to see that 1 over infinity squared is 0 versus infinity to the -2 is 0. They still are both true. And again, equals here, equals is, right, they're not really equal, it's getting closer and closer to, but we kind of say this. But yeah, that's why I definitely recommend writing it like this and not like this, because it's more of optimal.
And I have another question, like in our class, like another one of the indeterminate forms was like 1 to the.
Yep, we're gonna get there.
Yeah,
Okay, yeah, that's where we're about to get there actually. So there are, let me just list them real quick. There are a bunch of different types of indeterminate forms. Oh, do I have an example of that somewhere? So here are some other indeterminate forms that you should be aware of that we're going to talk about. Indeterminate forms. You have your classic infinity over infinity, 0 over 0, infinity times 0. In each of these, no, that's not true. And then you also have your infinity minus infinity, your infinity to the 0, your 1 to the infinity, and your 0 to the 0. Now, again, when we say these things, we don't really mean 1 raised to the infinity power. We mean a number that is very, very close to 1 being raised to a very, very large power. Similarly here, a number that's very, very large being raised to a power that's getting closer and closer and closer to 0. Okay, so let's look at some examples of these exponential forms, because these are the ones that require a little extra work. I had a really good example of that. I'll have to look for that. Yeah. Okay. Anyway, so let's say we want to find the limit as x goes to infinity of x to the, oh, is this that? Okay, fine. That example is fine. This example is kind of funky, but it's fine. X to the 1 over natural log of x. So there's a couple ways of doing this that are both correct. Some people prefer to do this. They like to write it as the limit as x goes to infinity of e to the natural log of whatever you've got. I'm not actually changing it. I'm just rewriting it like that. And the reason we do that is so that then we can bring this exponent down in front of the natural log of x. That's the whole reason for doing this, right? Whenever you have one of these exponential forms, we want to make it not exponential. So we do this to bring that exponent out of the exponent. So I'm going to rewrite this as the limit as x goes to infinity of e to the 1 over natural log of x times the natural log of x. This is kind of a silly example because what ends up happening here is the natural log of x is just cancel. And you get e, the limit as x goes to infinity of e to the 1, which is just e. Okay, this is one way people like to do it. Let me show you the other way people like to do it. Or some people like to look at the limit as x goes to infinity of just the natural log of whatever you were looking at before. Now, here's the thing. We're going to get an answer here, and that's not going to be our final answer. Our final answer, so this is going to equal some number. And our actual answer is going to be e to that number. Right? Because we did a natural log, we have to undo the natural log that we did by doing the exponentiation of that. I tend to prefer this first way because it feels like it's less clunky, but either way is fine. And some professors definitely teach it this second way where you take the natural log, you do your stuff. So bring down the 1 over natural log of x times natural log of x, and then that's just equal to the limit as x approaches infinity of 1, which is 1. But then your actual answer is e to the 1, which is e. Either way is fine. You still get e in either case. So let's look at some more examples.
How do you do with infinity minus?
We'll get there. I'm trying to remember there's an example I have. Yeah, there's an example I have that I don't love. We'll think about that. I'll try and come up with one while we do this over here. Let's look at the limit as x approaches 0 from the right of classic x to the x. 0 to the 0. And one thing I want to point out. No, I don't actually. A lot of the time 0 to the 0 ends up being 1, but not always. So not guaranteed, it's not guaranteed to be equal to anything really. So I'm going to write this as the limit as x goes to 0 from the right of e to the natural log of x to the x, which is then going to be the limit as x goes to 0 from the right of e to the x times natural log of x. Now, notably, my exponent here is a 0 times a negative infinity. I want to point out 0 times a negative infinity. Wow, that's really tight. Sorry. Can't really see that very well. I apologize. Bless you again. So just like before, when we had the 0 times infinity, we have to rework that still. So what we're going to do is we're going to write this limit as the limit as x goes to 0 from the right of e to the, instead of x times natural log of x, we're going to write that as the natural log of x over 1 over x. Using our standard kind of thing we do when you have a 0 times infinity, is you bring one of the things down to the denominator as its reciprocal. Usually the easier thing, unless it's e to the x, and then you bring that down. So then we use L'Hopital's rule. I don't think you need to. Some people like to write where you bring the limit up inside the power. Like you could totally write this as, if I don't use L'Hopital's rule first, you write this as e to the limit as x goes to 0 from the right of the natural log of x over 1 over x. I don't think you need to take that step to use L'Hopital's rule, but certainly people. That's what we're actually doing, because when you have a limit of e to the something, it's just e to whatever the limit of the something is, because e to the something is a continuous function. And limits pass through continuous functions. This kind of the stuff. This is one of those rules we talked about way back in chapter 1 or 2, where we said we have all these limit rules and we kind of use them all the time. This is one of those instances where we're using a limit rule and saying, oh, the limit of a continuous function is the continuous function of the limit. We're passing that limit through.
That's kind of just like doing it the other way.
Right. But totally, exactly. You're 100% correct about that. That is a good observation for sure. And so then we use L'Hopital's rule, and we get e to the, let's see, we still have to write the limit after you use L'Hopital's rule. That limit is still there. The derivative of the natural log of x is 1 over x, and the derivative of 1 over x is negative 1 over x squared. I do encourage all of you, because 1 over x, I feel like its derivative comes up a lot with these L'Hopital's rule questions. I definitely strongly recommend for everyone to get comfortable with saying the derivative of 1 over x is the derivative of x to the minus 1, which is minus x times to the minus 2, which is minus 1 over x squared. It is often convenient to write it as minus 1 over x squared. So then simplifying, I get e to the limit as x goes to 0 from the right. 1 over x divided by negative 1 over x squared is the same as 1 over x times negative x squared over 1, which is really just e to the limit as x goes to 0 of negative x, which is just e to the 0, which is just 1. A lot of work for 1. We get 1.
Why negative? Oh, because then it's gonna be x to the negative 1. Okay.
Right. So right, I've got 1 over x times negative 1 over x, or divided by negative 1 over x squared, which is 1 over x times negative x squared over 1. And this part just simplifies to negative x. And then I plug in 0 for x, and I get e to the negative 0, which is e to the 0, which is 1. Most of the exponential form, indeterminate forms, play out this way, where you use the natural log, you bring the power down, you bring it's reciprocal down to the bottom, then you use L'Hopital's rule, then you get an answer. That's often how these play out. So if you see a limit with an exponent, you often want to just try tackling it by doing those steps. Let's say we have sine of x to the 1 over x. What I really should point out here is this isn't an indeterminate form. If we plug in our 0, what's sine of 0? What's 1 over 0 going to? 1 over a positive 0. Right, infinity, definitely infinity. Okay, you have a 0 to the infinity. Now, you can logic your way. I feel like we can logic our way through this to say what the answer is. If you have a number that's 0, we're getting closer and closer to 0, it's small. And if you multiply a small number that's close to 0 by itself over and over and over and over and over again, it's just getting smaller and smaller and smaller. This limit is 0. So I want to really stress 0 to the infinity is not an indeterminate form. You can totally just evaluate it by saying 0 to the infinity power is 0. And that's totally fine. I feel like there's something else I want to say here. No, not really. Let's look at the thought. Well, that's an interesting thought that I've never had before. Huh. We'll come back to that. Let's look at the classic standard example. Limit as x goes to infinity of 1 plus 1 over x to the x. This limit should look familiar to you. It's okay if it doesn't, though. This definitely is the limit. This is actually how the number e is defined. E is defined to be this limit. 1 plus 1 over x to the x power, or 1 plus 1 over n to the n power as n goes to infinity or as x goes to infinity. I might have done an example, I don't know, where you take, like, I lend you $1 and I charge you 100% interest, and then we start calculating the interest, compound interest with more and more compounding. And as we compound more and more and more and more, as we take the limit, as the number of times we compound goes to infinity, that interest I earn ends up getting closer and closer to the number e. But we can also show it. So we don't actually just have to say it's e, we can actually prove it's e by doing the work. Oh, I should point out, right? This is definitely a 1 to the infinity form. And I want to really, really tell you 1 to the infinity is not 1. It's a number really, really close to 1 being raised to a really, really, really large power. If you plug in, like, if you plug in numbers, like if you do something like 1 plus 1 over 1,000,000 to the millionth power, just to check, it's going to be about 2.7. I really want to check, but I'm very confident because I've done it for other smaller numbers, and you already get the 2.71 when you're like 365, you're pretty close to 2.68, I think. So definitely going to be close to 2.7, but you should check on your own. It's a good thing to check. Well, let's actually do it. So doing this, I'm going to rewrite this as the limit as x goes to infinity of e to the natural log of 1 plus 1 over x to the x. And then we're going to do the usual 2 steps. We're going to bring the x down in front of the natural log. So it's going to be the limit as x goes to infinity of e to the x times natural log of 1 plus 1 over x. And then we're going to bring that x below the natural log as it's reciprocal. So we're going to rewrite this as the limit as x goes to infinity of e to the natural log of 1 plus 1 over x over 1 over x. Those are the usual 2 steps when you're dealing with an exponential indeterminate form. Is you bring that power down. I should say 3 steps. You take the e to the natural log, then you bring that power down, then you bring that power down below as reciprocal. I feel like you can go straight from here to here without doing this intermediate step if you're careful, but just be careful. So then we're going to actually use L'Hopital's rule because we can. Because now that exponent there is a 0 over 0 form. 1 over infinity goes to 0. 1 plus 0 is 1. Natural log of 1 is 0. And 1 over infinity is 0. So this top part definitely is, this exponent here definitely is a 0 over 0. And now we can use L'Hopital's rule. And get the limit, I'm sorry, use the wrong color pen, as x goes to infinity of e to the, all right, we have to take the derivative of the top and the derivative of the bottom. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of that stuff. And the derivative of 1 is 0, and the derivative of 1 over x is negative 1 over x squared. It comes up a lot. On the bottom, the derivative of 1 over x is negative 1 over x squared. Oh, look. Those negative 1 over x squared, they're going to cancel each other out. So we're left with the limit as x goes to infinity of e to the 1 over 1 plus 1 over x. And as x goes to infinity, 1 over x is going to go to 0. And you're going to be left with 1 over 1 plus 0, which is 1 over 1, which is 1, which is e to the 1. which is just E. Cool. I think that's really cool. More generally, and I do think it's worth saying this because this comes up a lot. Where does it come up especially? I don't know. It definitely comes up. Oh, it comes up in, it's in 21C specifically. More generally, you can say, you can show the same way the limit as x goes to infinity of 1 plus some constant divided by x to the x is equal to e to the k. And if you want to be even more general, the limit as x goes to infinity of 1 plus some constant over x to the x over some other constant is equal to e to the k over p. Kind of cool. It's the same exact work. You're just throwing in a couple extra constants that come along for the ride. But definitely, I've seen questions on tests, exams, homework problems where they're like, find the limit as x goes to infinity of 1 minus 3 over x to the 5x power. And I'm pretty sure the answer is going to be e to the negative 15th power. But we can check, right? We can do the work. It's going to be the limit as x goes to infinity of e to the natural log of 1 minus 3 over x to the 5x. We're going to bring the 5x down, and then down below is its reciprocal. So let's rewrite this as, interesting. I have a choice here. I'm going to make a choice. So I'm going to actually show both steps because here's the choice I would make. Bring it down as 5x times the natural log of 1 minus 3 over x. And then in my opinion, there is no reason to bring the 5 down to the denominator as its reciprocal. You could totally write it as the natural log of 1 minus 3x over 1 over 5x, or you could just leave that 5 up top, which I think I'm going to do. I'm going to write this as e to the 5 times natural log of 1 minus 3 over x over 1 over x. Bringing that x to the denominator as its reciprocal. And then we have a 0 over 0 in our exponent. So we use L'Hopital's rule. So we're going to get the limit as x goes to infinity of e to the, all right, same stuff as before. Excuse me. The derivative of 5 times natural log of 1 minus 3 over x is going to be 5 times 1 over the stuff times the derivative of the stuff. Okay, the derivative of 1 is 0. The derivative of negative 3 over x is just negative 3 times the derivative of 1 over x. And the derivative of 1 over x we've done 4 times already. It's negative 1 over x squared. So we're going to get negative 3 times negative 1 over x squared. You could also write it out, right? You'd be like, okay, negative 3 over x is negative 3x to the minus 1. And its derivative is positive 3x to the minus 2. Whatever you want to do, just be careful. And then the derivative of 1 over x is also negative 1 over x squared. And as is typical with these kind of problems, that cancels with that. And then if we simplify this, we end up with, let's see, the 3 over x goes to 0 as x goes to infinity. So we're left with e to the 5 times 1 over 1 minus 0 times the negative 3. Which is certainly e to the negative 15th power. Most of these exponential forms, your answer is usually e to the something. Sometimes your answer is e to the 0, which is 1. But other than that particular situation, which does come up relatively often, a lot of times you're getting like e to the 1st, or e to the 1/2, or e to the negative 15th. So you're getting a lot of e's in your, if your answer is an exponential form like this. Yeah.
So the whole thing where you like take all the stuff as fractions, like 1 over x and stuff, is that only for L'Hopital's rule?
Yes, it's always, well, I should say, I mean, yeah, I don't think there's other times we don't do it, but definitely for L'Hopital's rule, back to the kind of what the rule is, be able to use L'Hopital's rule, even though there are many indeterminate forms, we can only ever use L'Hopital's rule. Gosh, I know I wrote it down somewhere over here, right over here. We can only use L'Hopital's rule if we specifically have a 0 over 0 or an infinity over infinity type. So any other type, we cannot use L'Hopital's rule for first. I've definitely seen people over the years, like for example, I've seen people where we had like maybe say the limit as x goes to 0 of x squared times the natural log of x. I've seen people just say, well, it's in indeterminate form, and then they've just taken the derivative of the thing, which is not the right thing to do. You can't just take the derivative here. That's not what L'Hopital's rule says. So we have to rewrite. Well, first of all, we have to observe that okay, it's a 0 times an infinity. We have to rewrite this as natural log of x divided by 1 over x squared. And then it's a negative infinity over infinity. And then we can use L'Hopital's rule. But yeah, that's a very good observation. I mean, we always have to do this 0 over 0 fraction thing or infinity over infinity fraction thing before we are allowed to apply L'Hopital's rule. Let's see here. Now, problems all factors. I can't, there's an example I know I have. Let's see here. Okay, that example is not super exciting, but it's fine. Let's say we had, for example, this one's kind of boring, but I'm going to go with it because of what I've got off the top of my head for a second. The limit as x approaches, I'll think here for a second. Sure. Sorry, I'm thinking of a function. That's it. Let's say the limit as x approaches pi over 2 of tangent of x minus secant of x. Pi over 2 from the right. And from the right, sure, from the right, I guess that's fine. Okay. What kind of limit is this? What's the tangent of pi over 2? It's undefined. If we think about the right side of the tangent of pi over 2, so tangent looks like this. Pi over 2 is over here. Tangent does this kind of deal. So tangent of pi over 2 is pi, if you put pi over 2 from the left, this is actually going where? Negative infinity. And the same is true for secant. Secant looks a little bit different, but it also has a vertical aspect of pi over 2. It does this kind of deal. Like that. So it's also going to minus infinity. What's minus infinity minus minus infinity? Indeterminate. So this is an infinity minus infinity. It's just a negative infinity minus negative infinity. Or a negative infinity plus infinity or infinity minus infinity. So whenever you're subtracting infinities, they have to be the same type of infinity. If you have, just to point out, if you had like infinity minus negative infinity, that's not indeterminate. That's infinity plus infinity, which is infinity. Definitely determined, it just does not exist. But here, when you have infinity minus infinity or negative infinity minus negative infinity, we have to rewrite it as a fraction somehow. Now, with trig functions, it's not hard. We're going to just write them as sines and cosines. So here, I would definitely rewrite this as the limit as x approaches pi over 2 from the right. Let's see, tangent is sine of x over cosine of x, and secant of x is 1 over cosine of x. And then I would rewrite this as the limit as x approaches pi over 2 from the right of sine of x minus 1 over cosine of x. And now it's a 0 over 0. The sine of pi over 2 is 1, cosine of pi over 2 is 0. So now we can totally use L'Hopital's rule. I don't think you have to. I think it's a good idea too. Because if you do, so like if I just wrote this and didn't write that there, it said, okay, it's going to be equal to the limit as x approaches pi over 2 from the right of cosine of x minus 0 over negative sine of x. The person grading my work might not be aware of what I'm doing. They might not, or maybe I make a small mistake in my derivative, so it doesn't look like I've actually used L'Hopital's rule appropriately. I think writing this here is just a good safeguard so that whoever's reading my work knows that that's the stuff I'm thinking. Now if I plug in pi over 2, I get cosine of pi over 2, which is 0, over negative sine of pi over 2, which is 1. So I get 0 over negative 1, which is 0. So in this case, the infinities were about the same size.
So usually when you're given like a infinity minus. No, this is a. Sometimes it's not gonna be given, like you can't manipulate it by just doing instead of like hands.
Right. So there's another example. Let's see. There's an example I used to use that was really good. I can't see.
Thoughts, very common, like infinity minus infinity or.
I don't know about that. I've got another example. I mean, a question.
Like, is this rule that has the same sign also for like adding?
Well, so specifically, this rule about the signage only is when you're subtracting or adding. So, like, here are some indeterminate forms. So indeterminate, and I'll say you're probably not going to encounter infinity minus infinity very often. So you can either have infinity minus infinity, or I guess negative infinity minus negative infinity, which would be negative infinity plus infinity, but it's really just the same thing. Right, you're just changing the order of writing the subtraction or the addition. Here are some not indeterminate forms: infinity plus infinity, infinity minus negative infinity, negative infinity minus infinity. None of those are indeterminate. Infinity plus infinity is infinity. Infinity minus negative infinity is infinity. Negative infinity minus infinity is negative infinity. If you're doubling up on the direction of your infinity, you're just getting more infinite in that direction. You're not indeterminate. Sorry, I'm trying to think of this example that I know was good. Fine, we'll just do this. So let's say I wanted to find the limit as x goes to infinity of, sorry, I want it to be good. It's just going to be fine. Of x minus the natural log of x, which is for sure an infinity minus infinity. So what do? Well, when you're stuck with an indeterminate form, which we are, L'Hopital's rule is usually the only thing we can do. But to be able to use L'Hopital's rule, we need what? Yeah, we need a different form. Specifically, we need a fraction. So, fraction. Good call, James. I knew this problem was not the problem I want. I'm like, what's the problem I was thinking of? I don't remember. How do I get this as a fraction? Yeah, what do I do here? Good question. So what would I do here? I don't know. Might be stuck. For real. I mean, I know what the answer is. I know the answer is infinity. But how do I know that that's actually like useful? Well, what if I did something silly like this? Now, I really need to go find that problem that I'm actually thinking of. I could write this as x squared over x minus, well, that's not going to help. I'm just doing weird stuff now. Or like technically that's true. And I can write it as one fraction. I don't think that's really helpful.
Then you wouldn't get, oh wait. Would you get infinity over infinity?
Yeah, that's a good question. I don't know because it's
Infinity.
infinity minus infinity over infinity is yeah, it's dicey. What did I do? Came with a problem that's hard. So here's what if I wanted to actually say what this limit was without being very rigorous, because I've actually asked myself a question I don't know how to answer right off the bat. I know that x grows much faster than the natural log of x. So I know that this is going to be an infinity because this is much bigger than that. So what if I tried this? Let's write it as, so this seems like garbage. Let's try this instead. Let's try factoring out an x.
What is that? It's 3 times 1 minus.
natural log x over. Well, I know that this limit's 0.
Can you like move the x to the denominator, but add a power of -1?
Like, what do you mean? Yeah, no, I'm not sure what you mean exactly.
1 minus ln of x over x, all divided by 1 divided by.
Oh, like all over 1 over x? Right, but I have infinity over infinity here. So I feel like we could say this limit's going to be 0. We could actually use L'Hopital's rule. So it is true by L'Hopital's rule that this limit as x goes to infinity of the natural log of x over x is equal to 0. That is a true thing, right? Because we would just get the limit as x goes to infinity of 1 over x over 1, which is certainly 0. And I guess you could argue that that's going to 0, 1 minus 0 is 1, and infinity times 1 is infinity. Seems a little weird. I don't really love it. Like it could have done something else. But yeah. Now, I'm flustered because I know there's actually a better version of this problem that actually like makes you do something not terrible that I've just done. But that's what I came up with on the fly, so that's what you got. Let's look over here real quick. There was something else. Yeah, let's look at that. Oh, I had one other problem. Let's go back to the exponential forms for a second. So actually, I should back up for a second. You're not going to see a lot of infinity minus infinity. Like it's just not a thing that people typically ask about very often. Looking at some of the homework assignments I've seen, haven't really seen any infinity minus infinity. But let's look at something like this. The limit as x approaches 0 from the right of, where'd you go? Sorry. I had this. Yeah. Cosine of x to the 1 over x. Is this even indeterminate? I think so. Cosine of 0 is 1. 1 over 0 is infinity. This is a 1 to the infinity, which is indeterminate. All right, so let's do the usual, yeah. No, that's a good question. It has to be 1. Because any other, so if you're approaching any other specific number raised to a very large power, like if you had a 2 to the infinity, that's just going to blow up. Because a number that's 2 or getting very, very close to 2, right? 2 times 2 times 2 times 2. Whereas if your number was getting close to something that was a little smaller than 1, like 1/2, 1/2 times 1/2 times 1/2 is just getting smaller and smaller and smaller. So 1 is the only one that really is the one that matters. Yeah, that's a good question. So here we're getting the limit as x approaches 0 from the right of e to the natural log of cosine of x to the 1 over x. And when we bring the 1 over x in front, it really is just 1 over x times natural log of cosine, which is just natural log of cosine x all over x. So we're going to write this as the limit as x goes to 0 from the right of e to the natural log of cosine of x all over x. Oh, yeah, 0, yeah. Okay. So let's see what happens. Well, let's make sure we can use L'Hopital's rule. So here's the thing. If you're doing this whole deal here, it's always, if you've got the right kind of indeterminate form, it's always going to work out that you can use L'Hopital's rule. And here's kind of why. I think this is worth seeing. So whether you have a 1 to the infinity or a 0 to the 0, or what's the other one, infinity to the 0, when you take the natural log and bring down the power, you always get something that's going to be something you can use L'Hopital's rule for. Here's what I mean. if you do the natural log of 1 to the infinity, you bring down the infinity, you've got infinity times the natural log of 1. And if you divide by that, you've got divide by the reciprocal, you've got natural log of 1 over infinity, which is exactly a 0 over 0 form. Natural log of 1 is 0, 1 over infinity goes to 0. And the same is true if you do it for this one as well. You've got the natural log of 0 to the 0, and you bring the 0 down in front, you got 0 times natural log of 0, which is then natural log of 0 over 1 over 0. Natural log of 0 goes to negative infinity, 1 over 0 goes to some sort of infinity. And the same would be true for infinity to the 0. Kind of cool. And these are the only 3 forms that works for. It's kind of cool. It's kind of weird. It's kind of cool.
So when you do that, like, I mean, you can double check or check, but you just kind of know.
Right. So if you start off with the right kind of form, we know that taking the natural log will lead to something where L'Hopital's rule can be applied. We can also check though, right? Here, cosine of 0 is 1, natural log of 1 is 0, and the bottom's also in 0. So we definitely have a 0 over 0. As we expected when we started with a 1 to the infinity, it led to a 0 over 0. So now we use L'Hopital's rule. And we get the limit as x approaches 0 from the right of e to the, let's see. I shouldn't even write the bottom part here because the derivative of x is just 1, but I already did, so the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And so we're left with the limit as x goes to 0 from the right of e to the sine x over cosine x, which I guess you could write as tangent x if you really wanted to. Oh, thank you. Yeah, good call. Negative sine x over cosine x. And if we plug in 0, which we always should do before we do anything else to see if we need what we do next, we plug in 0, I get e to the 0 over 1, which is just e to the 0, which is 1. Which I would say is atypical. Often for a 1 to the infinity type, you usually end up getting something larger than 1. But not always. Kind of neat. All right, I should stop talking, let you all go. Class on Thursday, and that's it. You all should let me know what you would like to do on Thursday. I guess we should do some sort of review for your final.
And
A little bit of everything. If you want, so you all should, yeah, I'll try and think of stuff. If you want, if there are specific topics you want me to focus more on, I certainly can. But I'll try to be exhaustive, but we only have a couple hours today. Yeah.
no co-class next week.
No, there are no classes at all next week. No co-classes, no regular classes, just finals. But so that said, all of us, myself, Sarah, Grant, the other math specialists, we will all be available in the drop-in in the library Monday, Tuesday, Wednesday, Thursday,
Oh, in
Friday.
the lower.
Yep, where all the drop-in is. We'll all be there. So if you're looking for myself or any of the rest of us when we're not doing things, that's where we'll be. And our schedule should be posted on the AATC website soon, if not already.
You keep it like on a co-class like that? No.
Nope. That is not what my job is. The people that teach the actual classes are the professors and the grad students and the postdocs and all the faculty, which I am not. I am staff. You're welcome. What's up? Let me see. What am I saying? Sure. Where am I signing?
You could just sign it like next to the office hours for like your information.
Okay. Anything else?
Nope.
Cool.
Thank you.
You're welcome. Oh, look at that. Yeah, what's up?
I was like, honestly, I trying to check like the main thing, like for the class.
Okay.
Review. And like the list was like hanging off with like derivatives, actual
Sure.
delta,
Sure.
functions and like their
Thank
derivatives.
you.
You're welcome.
Then related rates and optimization, because I think my teacher put like. what
Sure.
it looks like.
See that?
then inflection points, and then concavity.
Mhm.
And based on like the first and second derivatives, you get like most of like concavity inflection points increasing, decreasing.
Yeah,
Would you say that's like a good list? of this
yeah, I
scenario?
think so. Yeah. You said derivative rules, right?
Yeah, derivatives.